In this video, we're going to take a look at linear approximation. For our first example, let's find the linearization of the function cube root of x, and let's do that at the point x equal 125. So first thing we need to do is think about this word here, linearization. What we're doing is we're finding an approximation of our function. And this approximation, this formula, is a formula that we should be familiar with. The formula says that f of x is approximately f of a plus a little bit of error, and that error looks like a derivative times a small change in x. So I'm going to put a box around this. It's a formula that we may need to write down a few times before we get the hang of it, but the idea here is pretty important in helping us to remember the formula. We're saying f of x is pretty much f of a plus a little bit of error. So hopefully that will help you in remembering the formula. If you think back to our previous video about differentials and error, you might remember that error always looks like a differential. So in other words, it's derivative times a small change in x. So that's a good way of thinking about this formula. A here is a constant. So it's just some number that comes up in the problem. All right, well, let's see if we can pull out all the information that we need. The function that we're working with here is the cube root function. We may want to write that as x to the 1/3 for the purpose of taking the derivative. We're going to also need f prime of x. So f prime of x is going to be 1/3 times x to the minus 2/3. And we may want to simplify that a little bit for the purpose of doing our calculation here. So this is going to look like 1/3 times. Well, this negative exponent here is going to cause our x to the 2/3 to come down into the denominator. And the exponent 2/3 here is going to correspond to a cube root, and then our quantity being squared. Okay, so that's how we can rewrite our derivative here. So the negative exponent brings the quantity down into the bottom. The 3 in the power, the denominator in the power, corresponds to the type of root, and the numerator in that exponent there corresponds to just a power, a regular power on our expression. Okay, now we need to figure out what our value of a is in this problem. And it's always the wording here that makes things a little bit tricky. In this problem, it's asking us to find the linearization at a particular point. And this point here is always given as x equals a. So even though it reads as x equals 125, it's really giving you the value of a. Okay, so in this problem, a is going to be 125, x is going to stay as a variable. That's always a little bit tricky the first time you see this. So f of a represents the cube root of our a values. So cube root of 125, which is 5. And f prime of a represents the value that we get when we plug 125 into this expression here. So 1/3 times the cube root of 125 all squared. Okay, so that gives us 1/3 times. Well, the cube root of 125 is 5. Then we square that, we get 25. So we've really got 1/75 here. So that's our value for f prime of a. All right, so now we're all set to go back to our formula here and just write down our linearization. F of x in this problem is the cube root of x. So we're saying cube root of x is approximately 5 plus a little bit of error, and that error looks like our derivative, the 1 over 75, times a small change in x. So x minus a. All right, so that is our linearization right there. Now, a couple of comments here just to help us understand what's going on here. First of all, this approximation that we're getting, this approximation will be better the closer x is to 125. Okay, so if you try plugging in x equal 125 here, this big term on the right is going to be 0, and we will have an exact equality here. Cube root of 125 is exactly 5. So at x equal 125, even at nearby points like x equal 126 or x equal 124, it's reasonably good. The approximation will get worse as we plug in x values that are further away from 125. And this partly explains the wording of the question here. Give me a linearization that's going to be good when I plug x values near 125 into it. So let's try just to remember that a is a number that's being given in the problem. X remains as a variable. The second comment here really goes to applications. Linearizations are really useful in more advanced calculus courses. So if you go on to another calculus course, you will use linearization to help you calculate areas and volumes, particularly when our function is quite complicated. So this is really just sort of a more basic introduction to the subject to get us ready for more advanced courses. So in this example, let's approximate the square root of 15.07 using a linear approximation. Okay, and just to comment on the wording here. So this question could be worded as approximate the square root using a linearization. So that's another word that might come up. You might even see it worded as approximate the square root using differentials, because all three of these different ways of wording the problem really come down to our linear approximation formula. So same formula that we talked about in our previous question. This is our linearization formula. We said that f of x is approximately f of a plus a little bit of error, and that error looks like a derivative times a small change in x. Okay, and a is just a constant that comes up in the problem. So it helps to write out this formula a few times. That's probably the best way of just getting it down, is trying a few problems and just writing out the formula each time. Okay, well, let's see if we can make sense of what the question's asking. We're going to do a little linearization here, and in this problem we're actually going to be able to plug in a specific x value and figure out how good our approximation is. So the function that we're working with in this problem is the square root function, because we're being asked to approximate the square root of some value. Okay, so we're working with the function x to the 1/2. The derivative of this function is going to look like 1/2 x to the minus 1/2. And if we simplify that a little bit, it's going to look like 1 over 2 And this expression here is going to come down into the denominator. It's going to now have a positive exponent, so x to the 1/2, or just a root x coming down into the denominator there. Okay, so that'll be useful when we go and plug in some numbers in a little bit. Now, in this problem, there was no a value given to us, so we're going to have to think about a. Just like in the previous problem, we want f of a to be an exact value. We want to make sure that when we plug a into our function, we're getting something really nice, like 1 or 2 or something to that effect. We don't want a long decimal expansion here. Just having a decimal would just destroy the approximation that we're doing here. So we need f of a to be exact, and we also need a should be near this number here, 15.07. Okay, and that is because our approximation is only going to be really good for x values that are close to a. So with these two ideas in mind, hopefully we can come up with the number a equals 16. That will be our choice here. All right, so with that, let's do our little bit of calculation here. F of a is the square root of 16, so that's going to be 4. F prime of a, if we look back over here, here's a nice formula for f prime of x. It looks like 1 over 2 times the square root of our number, and remember we're evaluating this at a, so plugging in a 16 there. We get 1 over 2 times 4, or in other words, 1 over 8. All right, and with that, we're ready to plug in then to our linearization or linear approximation formula. So f of x, our square root function, is going to be approximately f of a, so approximately 4, plus a little bit of error, and that error looks like our derivative times a small change in our x values. So we're going to go x minus a. Okay, and the idea is that this approximation is really best when x is close to a, so when x values are near 16. So it gets better as x gets closer to 16. It gets worse as x moves away from 16. Now, to come back to the goal of the problem here, we're really trying to calculate, oops, let's just highlight that there. We're really trying to calculate the square root of 15.07. So all we need to do now is just plug in x equal 15.07. We need to do that all the way through the expression. So we get 4 plus 1/8 times 15.07 minus 16. Okay, so we can grab our calculator here, work out what this number works out to. Comes out to exactly 3.88375 was what I got on my calculator. And we can now check this or compare it to what we get on our calculator just by grabbing our calculator and just doing 15.07 square rooted. Just do that directly. It works out to 3.882, and we get this long decimal expansion there. So the idea is that we look at these two numbers, they're fairly close, and that's a good thing. So at this point, this is sort of a simple way for us to check that our linearization works.